All right, welcome back. What we're going to do this time is we'll do limits of functions. I'll squeeze in an extra videos with extra computational. So last time we did transformations of functions and I said I would start off doing it this way, but I'm getting behind in the video posting and editing, etc. So let's do limits of functions, start this category or this topic, and then I'll do another video and I'll squeeze it in between 3.1 and it'll just say extra problems for this. And I'll do this regularly. I'll add videos for just extra computations in the playlist for Calculus 1. All right, what's the idea of limits? The idea of limits is goes back to the Greeks and Achilles. He's got an arrow, and this can be the idea. And then he's got a target. We'll just put a target, but he's shooting them at humans. And what he sees is when he shoots the arrow, he has a paradox seemingly because he knows that the arrow eventually will hit the target in its path. But then he's thinking about this and he says, well, what if I half it? And so for the arrow to get all the way to the end, it has to reach the halfway point of that interval, whatever that interval is. And then from there, it has to reach the halfway point of that interval. And from there, it has to reach the halfway point of that interval. And then the halfway, and then it seems like there would be infinitely many halfway points. And so for the arrow to reach its final destination, it has to meet infinitely many halfway points. And so then in one sense, in one way of looking at it, the arrow never reaches it. But clearly, as he shoots it, he sees that the target hits it. And the way we rectify this is with a limit. And that we're going to say the limit as the distance, the limit. Well, we won't put notation for this one, but basically what we're saying is the idea of a limit is as we get closer and closer to the target, the distance between the target and the arrow becomes zero. So the limit as the arrow, I'll sort of put this in the syncopated algebra, as the arrow approaches target, the distance between the arrow and the target is zero. And we're going to put, we won't put this horrible distance or words in there, but this is what we're going to do. We're going to do limits of functions of a single variable. Let's try that. So the notation we're going to get is given a function f of x, I don't know why this one's squeaking, which is y. What we're going to say is, and a point x equals a, possibly not in the domain, we'll get to this eventually. We want to say that we want a symbol for describing the fact that values of f, let's try a different one. That one wants to be Mr. Squeaky. I don't know if you can hear it or pick it up, but hopefully it picks me up and not the squeak of the pen over and over again. The values of f of x approach but never actually reach arbitrarily close, get arbitrarily close to, let's say it this way, f of x. The values of f of x get arbitrarily close to some number L in R as, but it never equals L. It never actually equals it. Touches L, we'll say, colloquially at first, as the values of x in approach A as close as we want. And we want a symbol for this. So the first thing you should know is we did graphs of functions, and then we did special types of functions and their graphs, and then we did transformations of moving them around on the plane. Now what we want to do is, given the graph of it, we want to start describing what's happening with when we approach a value in the domain, or not in the domain, but as we approach a value in the horizontal, we want to know what's happening to the function in the vertical. And what this is going to say at first, there's going to be several different kinds of limits, but for the first idea of a limit, we're going to do a finite limit at a finite value. Let's describe that in, approximately speaking, the more rigorous definition of what they mean by a limit. All right. Let's look at an example first, and then we'll look at the definition right below. So f of x equals x squared plus 1. And let's do g of x is 1 over x. And let's let a equals 0, the value we're going to approach. For the first one, let's see what happens. So we're going to see what happens as we get closer and closer to 0 with this function. If we took values, we could say that we could take, say, 0.1 or 0.01 or 0.001, and we're going to take smaller and smaller values which are approaching 0. They're getting smaller and smaller. They're getting closer and closer to 0. And then we could see what happens to f of x, which is x squared plus 1, or g of x, which is 1 over x. Let's do it that way. As we do this, 0.1 squared is 0.1 times 0.1, which is going to be 0.01. And then so plus 1 is our function. So we're going to get values that get closer and closer to 1. This one will be 0.01 plus 1, which is getting closer and closer to 1. And it seems like as we draw these, and we can use the picture at first to cheat, we should know as standard functions, what is this? This is the standard function x squared, and then it's been shifted up 1. So we know it should look like a u, and then it's shifted up 1. So there's the standard transformations from last time that I used quickly. 1 over x is just one of the standard functions, and it looks like this. And there's problems. So we're going to have to try and describe what we're saying here. X squared plus 1 just seems like as x gets closer and closer to 0 from either side. This time I picked positive values, but you can pick negative values also. You could pick negative 0.1 and negative 0.01 and negative these guys. Oh, and it seems like my function gets closer and closer to the value 1. And that's what we're going to say, and that's what the symbolization that we're going to use once we see that. We're going to say that the limit as x approaches a, so let's color code this. We're going to use this symbol limit. And then what are we going to do? The most important thing is where you're going. So x is approaching 0 is where we're trying to approach. And then what we want to say is that's of our function now. F of x, we want to say approaches, in this case, equals L. That's would be the general, in our case, I'll write the general one right after this. In our case, our L will be a 1. In this case, it seems like it blows up arbitrarily large and from the right, and this one says that it's going to blow up arbitrarily negative to the left. So now in this case, this function is behaving way different than this function. This one's just approaching a nice value, which is a real number. And we're going to have to say something about this one, which will be infinite limits and when we're approaching finite values. I'm still approaching 0 from both directions, but our function is not defined there, so it's going to blow up. And we want to describe whether it's going to blow up positive or blow up negative. We'll get to that one in the next video. For now, just in the introduction, we'll stick to finite numbers. But this one seems like if we do 1 over 0.1, that's 1 over 1 over 10. If you put it in a fractional form, that's 1 over 1 over 10, which is 10. If I do 1 over 100, I like the fraction avatar a little bit more. If I do 1 over 100, this will be 1 over 100, which is 100. If I do 1 over 1,000, which is getting closer and closer to 0, it seems like my value is approaching 1,000. So it seems like this is getting arbitrarily large or approaching infinity as the values of x, if we use positive values. If we use negative values, it would do the exact same thing, this one, except it would approach negative 10, negative 100, negative 1,000. And so it's telling us that it's blowing up arbitrarily negative when I approach 0 from the other side, from the negative side. And then we'll say the limit doesn't exist, but we'll have to get into a bunch of caveats. Let's erase and describe the definition of what we're trying to describe here in general, and then we'll do a few examples. Remember, we're getting arbitrarily close to it, but never actually touching it technically in the limit. All right, definition. We will write the limit as x approaches a of f of x equals L if and only if, by definition, the values of f of x get arbitrarily close to L in R, but not equal to as x gets arbitrarily close to A, but not touching A. So we're getting as close as we can, and you can add more half intervals in that limit where the arrow's approaching the target. You can add those, but we're never going to actually touch the limit. We'll get into that when we actually touch the limit and L equals f of A. That will be continuity, and we'll talk about continuity. And continuity will be a limit definition, but it has a special condition on when you're continuous versus the limit existing. As an example, let's do find the limit as x approaches let's say 3 of, let's do 1, I'll make it an easy one, of the function f of x equals x squared minus 1 over x minus 1. I won't draw it for you. I'll do the algebra first, and then I'll show you what's happening with the picture. Well, maybe I should draw it first. As we start this, let's ask ourselves, first of all, where am I going? I'm going to 1, so this is the most important part right now. X is approaching 1, and we want to know what number L, if anything, that this limit is going to approach as I approach the value 1. And what the first technique that you're going to like is if there's algebra that will clean us up, then the algebra will help us compute the limit. What we're going to say is the limit as x approaches 1 of x squared minus 1 over x minus 1. And now I ask myself before I start preliminary, what's the domain of this? We know that the domain of f is, I run my mantras, I have division by 0, so x can't equal 1. So this would be negative infinity to 1 union 1 infinity. Everything but the number 1. And then when I do simplify this, if I use this cleverly, x squared minus 1 over x minus 1, and I realize that this simplifies into a difference of squares of x minus 1 over times x plus 1 over x minus 1, I can get rid of that algebra discontinuity. But the domain, because it was originally given as this expression, the domain still says that even though it looks like now that it's just a straight line, we have that, in fact, the domain is still, you can't equal 1, so there's a hole in my function. So if I look at this function, y equals x plus 1. So my mantra will be eventually, if you're not picturing the graph of a function near a value, you're doing the limits wrong, because that's what they're trying to describe with this algebraic business. Ooh, careful. Now what do I have? What is x plus 1? When x is 0, y is 1. And when y is 0, x is negative 1. We're going to get this. And then at 1, though, it turns out it should be the value 2. But we have a hole in our function. So this is the graph of x squared minus 1 over x minus 1. And that's why the picture's worth 1,000 words. When we do this, you want to see that we're going to approach I used orange, I think, here. As we approach the y value of 1, or sorry, the x value, we're going to approach, get arbitrarily close. Where is now, what I'm asking is, where does the function approach? And it seems like it's 2, and because we use algebra, you can just put, once we have no problems where I'm going, you can just put the value into the limit, and that will tell us that the limit was 2, but you can't actually equal 2 in the function. There's a hole there. That's the difference between the limit existing and continuity. For now, let's just practice computing these limits. And this one will work out nicely the way you want. Algebra will help us and save us. So this one will say this is equal to the limit as x approaches 1 of, I do the same algebra, x minus 1 times x plus 1 over x minus 1. That algebra cleverly is going to get rid of the discontinuity. I write it out, and yes, you have to write the whole limit every time. You can't simplify. So this is x plus 1. Now I check where I'm going 1. Is there a problem? No. So I can just evaluate the function at that value. This will now be equal to 1 plus 1, which is 2. So the limit, which is the number L, which is in R. And now, again, what that's saying is our function is getting arbitrarily close to the value 2 as our function gets arbitrarily close to the value 1. But technically, in this case, 1 was never in our domain, so we can't equal 1. So we never actually touch 2. There's a hole, but we can get arbitrarily close to it, and that's what we mean by the limit is 2. We'll get there. Same as when we do speed of light, etc. Here's the speed of light c. We're allowed to approach the speed of light. Things with matter are allowed to approach the speed of light from below, but you can never ever touch the speed of light, because if you touch the speed of light, I can show you later when we do some more of these left-hand limits and right-hand limits, we'll see that your mass will become infinite and your length will become 0 in the direction that you're traveling the speed of light. So again, in limits, this is a nice idea. You can approach the speed of light, but you'll never actually touch the speed of light. And in these ones, it'll give us a good idea of left-hand limits, right-hand limits. For now, let's end here, and then I'll do another video which tells us how to use the rules and then what algebra you can use to simplify all of these limits, and then we'll get into the different types of limits. Let's do that one next.